We've seen that in neural networks, the output of a neuron from one layer is connected to the input to a neuron in another layer, in the layer that follows. There is a connection weight W for this connection. What determines the value of this W? I'll be the first to admit that neural networks are a little hard to understand, especially when you encounter them for the very first time. Back when I learned neural networks and how to build them, what really helped me was understanding what exactly a neuron was and the concept of the neuron as a learning unit. So let's dive right into that. We ended the last lecture at this neural network where every layer within this neural network was made up of a bunch of neurons, and neurons from one layer fed its output to neurons in the next layer. Let's now understand how a single neuron operates and what exactly it does. The simplest way to define a neuron is that it is a mathematical function. It's a mathematical function that can receive a number of different inputs. These inputs are represented by x1 through xn that you can see on screen. It performs some kind of operation on these inputs, some mathematical function. At this point, it could be basically anything: addition, subtraction, multiplication, calculus, you name it. The inputs to the neuron serve as inputs to this mathematical function, and the neuron produces a single output represented by y. This single output then can be sent to multiple neurons in the next layer. Now, this neuron is said to be active or is said to contribute towards the machine learning model if a change in the inputs to this mathematical function triggers a corresponding change in the outputs. Now, if this neuron is such that you change the inputs in any way you want and there is no corresponding change in the output, this neuron can be thought of as being dead or inactive. This output Y produced by a neuron is then connected to several other neurons in the next layer. Here we visualize a single connection to one neuron in the next layer. This neuron from the second layer is also a mathematical function, and this Y output of the first neuron serves as the input to this second neuron. Every connection between two neurons in subsequent layers is associated with a weight. A weight is simply a multiplicative factor that is applied to the output of the first neuron. This weight basically represents how strong this connection is between the first neuron and the second neuron. Remember that the second neuron will receive inputs from all neurons in the preceding layer. Here we show just one input to the second neuron. There will be many as there are neurons in the first layer if this is a fully connected neural network. This weight associated with every connection between neurons is a measure of how sensitive the second neuron is to the output of the first neuron. If we find during the training of this neural network that the output of the second neuron is very sensitive to the input of a particular neuron from the previous layer, the connection between them gets stronger and the weight W associated with this connection increases. This can be expressed slightly differently as well. If the output of the first neuron causes the second neuron to fire more strongly, the connection between them is stronger, the weight associated with that connection is higher. This has also been described as cells that fire together, wire together. In the real world, when we build a neural network using these neurons, a single neuron is generally connected to multiple neurons in the next layer. Every connection will have its own weight. Depending on how strong that connection is, depending on how sensitive the neuron in the second layer is to changes in the output of the neuron in the first layer, these weights will be different. And the entire concept of training this neural network is to find these weights of the connections between the different layers. Once a neural network is fully trained, all edges within the neural network have weights, and it is these weights which help the neural network make predictions. We know that a neuron is essentially a mathematical function. Let's now peek inside a single neuron and see exactly how it operates. Neuron applies two very simple mathematical operations to its input. The first is the affine transformation. The affine transformation is fed in a number of different inputs. It produces an output which is then passed to an activation function. And that's it. This affine transformation and this activation function is all the math that is applied to the input of a single neuron. And each of these functions by itself is very, very simple, as we'll see in just a little bit. We'll start off by understanding the affine transformation because we've studied this before when we studied the linear neuron. The affine transformation can learn only linear relationships between the input and the output. The affine transformation alone is enough to learn linear regression because the only relationship it represents is a linear one. Now, it should be pretty obvious that a neural network made up of these neurons can't perform all the magical stuff that it's supposed to unless it can understand more complex relationships. And that is where the function comes in. The combination of this affine transformation and activation function allows the neuron to learn any arbitrary relationship between the input and the outputs. Let's look at the input to this affine transformation. There are a number of different x inputs represented by x1 through xn. Each of these inputs is associated with a weight. Remember, the weight determines how strong the connection is between this neuron and the preceding one, which fed it its input. The affine transformation also takes in another input b, which is essentially the bias, which allows you to shift the linear relationship in space. The output of the affine transformation is a relationship which can be expressed using the formula Wx plus b. The affine transformation is just a weighted sum with a bias added. Now, a good question to ask here would be, okay, we've understood that x1 through xn are the outputs of the previous neurons, but where do we get w and b from? These weights and biases are what we determine during the training of the neural network. The whole purpose of the training process of a neural network is to basically converge on those weights and biases which allow the neural network to make the right predictions. These weights and biases are basically determined by the corpus of data that you feed in during training. There are, of course, other design factors that we have to take into consideration. We won't go into detail of those right now. We'll do so in subsequent lectures. The linear relationship doesn't require much explanation beyond this. It's pretty self explanatory, and we've done regression models, which means that you've understood what it does. Where we'll focus on is the activation function. That's in the next lecture. You should know, though, that this combination of activation function with the affine transformation allows this neuron to learn arbitrary relationships between the inputs and the output. If neuron 2 is connected to neuron 1 and the output of neuron 2 is highly sensitive to the input provided by neuron 1, then the connection between neuron 2 and neuron 1 becomes stronger. When the connection is stronger, the weight for this connection increases. So neurons which fire together, or neurons which are sensitive to another neuron's input, have a higher weight for that connection.